All right. Let's roll. Okay. Higher order derivatives. So here's the deal. Kind of mentioned this before in kind of in passing a little bit when we talked about when I was just told you, hey, you can if you take a derivative and get this new function, and like particularly with position, and this is something we're gonna keep going, but you can take derivatives multiple times is the idea, and so this is what higher order derivatives really are about. So a lot of times we just really just get to the second derivative because contextually, when it comes to like say position, position, velocity, acceleration, that's really as far as we can really understand it ourselves really well. Beyond that, it gets very difficult to really understand how that kicks in, but I could give a little explanation for what the third derivative would be as far as that goes. But so we have that, and then we also have uh, graphically speaking. As far as graphically speaking goes, we really just mostly talk about at the second derivative level what it represents graphically. So it's something that isn't a huge deal to go past it for the most part, but then there's a whole another aspect of calculus where we go, really, we could do it for just as many times as necessary. So we could do higher order derivatives really sometimes to no end. So, but let's just start off with like say a position function. So S is usually what we talk about when it comes to position is usually the one that they give. They might give x of t or y of t as well, but s of t is what we're going to start off with. So s of t, let's say we have, oh, all right, let's go with sine of x, or sine of t, I'm sorry, because it's s of t. So sine of, okay. So this is our position. All right, so position is your first one. That's your original. If we took the derivative of position, then we get velocity. That's right, v of t. So what's the derivative of sine of t? Cosine of t. All right, and that's velocity. And so this is our first derivative. Okay, first derivative. All right, then we could take the derivative again. So now we have s double prime. So yeah, so s double prime. Okay, so s double prime, which is v prime. And the derivative velocity is acceleration. And the derivative cosine of t would be negative sine of t. And we get there. Now, so this is acceleration, which is our second derivative. And that's how we note it there. Now we could also do a third derivative as triple prime of t, which would be v double prime of t, which would be a prime of t. And that is what we call the jerk. So this is where you are. Okay, so imagine you're in a car. Okay, so you're in a car. This is where you are. Okay, here we go. Here we go. So let's say that in an airplane. Okay, you're in an airplane. So this is where you're at. This is like your location. This is how fast you're moving in the airplane. This is how fast you're accelerating in the airplane. And so you feel this, this you observe by just looking. Okay, this you can observe by feeling that the motion. Okay, this one you feel the force because acceleration is part of force. And so you have mass and if your acceleration, then you have force. And so you're feeling force, and if it's a nice constant acceleration, then it's a constant force. But if the acceleration changes and all of a sudden like speeds up, so let's say like in an airplane, they have they have the controller, and then and so what happens is as that happens, as their acceleration increases, you get jerked back. The acceleration is already pulling you, and so you can feel it. But then when the acceleration changes, then you get jerked back, and that's why they call it the jerk. Now, typically, we don't really talk much about this one, but this is what it is. So So this would be going forward. So now with this right here, we have all of these. These are just different things. Okay, and so you can find, let's say at, t equals, and let's pick a good value for all of this. Let's say, pi over 4. Okay, so t equals pi over 4. And we want to take a look at it. And so, okay, well, s of t, where s of pi over 4, well, that's sine of pi over 4. What's sine of pi over 4? Radical 2 over 2. Okay, that's where you're at. So that's the location. So imagine, you're just moving along the sine curve, and so that's what you're doing. Now the velocity at pi over 4, let's say that this would be, okay, and let's say that this is measured in feet. Well, for example, this could be, now there's lots, this is some distance measurement. This is a distance measurement. And so like feet or meters or miles or whatever. So let's say this feet. This is a velocity one, so this would be like feet per second. So it's distance over time. Distance over time. This one, a lot of times you'll see in math books, or they'll do the velocity, the feet per second over the time. So feet per second per second. You could actually change up that one if you do it that way. But most typically speaking, you'd have feet per second squared. And so this would be your distance over your time squared. Now, what do you think this one would be? Well, that's going to be distance over time cubed is how that would work out. But we can't really, it's hard to express that idea or to quantify how much you've been jerked back or even forward if you decide to push the brakes harder. Just imagine that, like you push the brakes, and so you are slowing down. You're applying force to slow yourself down. But then if you slam on the brakes while you're doing that, you're going to be jerked forward, and so you can feel that jerk as well. It'd be a negative jerk though. All right, so we got this v of 4, which would be radical 2 over 2, because cosine of pi over 4 is also radical 2. A of pi over 4 is going to be negative sine of pi over 4, so that's negative radical 2 over 2. And J, the jerk at pi over 4, would be also negative radical 2 over 2. Okay, so this is what's going on. And again, this would be, if for example, we got feet per second, we have feet per second squared, and feet per second cubed. Or you could also have done meters per second squared, and meters per second cubed, or miles per hour squared, miles per hour cubed, or even miles. So the t stays in the same thing. So there's lots of different ways you could do that. You could just pick different distance or time units to use. All right, now, so this is how we evaluate those. Now, and you can see it just kind of goes. And also, what do you think would happen if we did s the fourth derivative? And I'm going to show you actually how we write that. So that one, I do not know any name about it, nor would I have any way really to express it. But that is, such is the nature of humanity, is we're kind of trapped in our 3.5 dimensions, and it's really hard to start talking about things outside of those. But anyway, so the fourth derivative, we actually put the 4. Once it gets past the 3, we put the number up here. So as 4 of t, then if we had this, well, the derivative of cosine is negative sine, so we have a negative sine of t. And what do you think? You can see what's going to happen, right? It's going to sine, and then it's going to go back around. And so it's sine, cosine, negative cosine, sine, cosine, negative cosine, sine, cosine, negative sine. So that's just one of those things about sine and cosine, is that it just cycles around. It's reminiscent of the imaginary number to the different powers. So, but just want to throw that out there. Okay. Additionally, and this is a super important thing, because this one always comes up with the AP exam. And well, heck, I think you should expect to see it next Friday on your quiz. Not tomorrow, but next Friday. And so here's how this works out. So let's think about, we'll do a little Punnett square, velocity, and we'll do acceleration. Okay, so we have velocity and acceleration. All right, so the way it can work out, velocity could be either positive or negative. Acceleration could be either positive or negative. What's a positive times a positive? Well, that's positive. What's a negative times a negative? Well, that's positive. So those would both be positive, and these would both be negative, right? Right. Okay, you know how to multiply. Now, what this means then is that if the velocity, so this is real important, okay? If you don't write anything else down for a while, then write this down. If velocity and acceleration have the same sign, then the object is speeding up. There we go. If velocity and acceleration have the same sign, then the object is speeding up. What that means then is if velocity and acceleration are both positive, so imagine you're running this way, okay, and then you hit your nitrous, you speed up and you're going the same direction. Well, that one's pretty easy to understand. That if you accelerate going forward while you're running forward, you're going to speed up. Now, the same thing would be true is if, let's say, you're backpedaling. Okay, you're backpedaling. That means running backwards. You're running backwards, and then somebody pushes you in the chest, and that speeds you up. That's acceleration. You're speeding up going backwards. So if the acceleration and the and velocity are both in the same direction, you're speeding up. If they're in opposite directions, that's what's going on here. Opposite directions. So opposite signs mean what? The object is slowing down. That's the opposite. So the opposite of speeding up is slowing down. The opposite of the same direction are opposite directions. So that's pretty big. So think about it this way: if whichever way you're running, okay, and if somebody, let's say, somebody lassos you and pulls you, tries to pull you back, well, then their acceleration is opposite the direction of you. Okay, so, or if somebody's pushing you, you're trying to run and then somebody, starts pushing you, there you go. Or if you're driving along and then you push the brakes, okay, then your acceleration is backwards and your velocity is forwards. And so what's happening is you are slowing down. And this is big. We talk about this, okay? So let's take a look up here. Using that, okay, take that information, look up at this data, and make a conclusion about our object. Our object is going to be slowing down because velocity and acceleration have opposite signs. There we go. Okay, so there's something to do. And that, I think it's really important that we keep tying this back to, this stuff. All right, so let's take a look at some other ones here. Okay, now, so we could also have just your regular old functions. So we have y equals x to the fifth. Okay, so something like this. All right, so something basic. Then what we're going to do is, well, we could write this a couple of ways. We could either write it, let's just keep it that way. Y prime would be 5x to the fourth. Y double prime, 20x cubed. Y triple prime, 60x squared. Y to the fourth would be 120x. And how long do you think we could keep doing this? Well, technically we could keep doing this forever, but it gets really boring after a little bit. So the fifth derivative will be 120, and then the sixth derivative would end up being 0, and every subsequent one will also be 0. So we can write it that way. Another way that we also write this is we write dy over dx, like so, dy over dx, and then this would, so dy over dx would be the 5x to the fourth. That's your first derivative, okay? These are the same. The complement here, this we write d squared y over dx squared. And you see this a lot. We write this one a lot, okay? Which is 20x cubed. The reason for that is because basically this one was dy over dx, and then what we did is we did the d of dx of that thing. We have two d's, so that's d squared, and we have two dx's, so that's squared. That's the idea. But that's what they did there. Anyways, and so then the next one would be d3y over dx cubed, which is 60x squared. And then, of course, you have d fourth y over dx to the fourth. And you can see that the numbers just keep on growing no matter what, okay? And so let's say we have, and then we have Anyway, yeah, d fifth y. Sorry, I just disappeared right there. I am pretty darn tired. But yeah, so that's what happened there. My bad. Just sorry about that. Okay, so you see that it's just the same concept. It's just a different way of writing it. Technically, there is another way too that we see derivatives written. I don't. We sometimes somebody came up with this idea and it hangs around. These are the main two. Okay. We see these ones the most often. Very rarely will you ever see this. It'd have to be your university professor would have to be in love with that sort of notation for you ever to really have to worry about that. So this one, don't even worry about it right now. Okay, but I'm just letting you know it exists. But these ones here, these are the ones that we see the most often, and so be ready for that. Okay, so all right, so let's yeah, let's take a look. Let's do another one of those. Oh, yeah, and sometimes what you have to do is you might have to use some rules over and over again, which I know stinks, but it is what it is. So let's say we do y equals, or you know what, let's do f of x because we haven't written that guy again. So f of x, here's another example. So f of x equals, yeah, so sine of x over x. Okay, remember this one? All right, we talked about this one in the last one. So f prime of x, in case you forgot, is x bottom times derivative of the top, x cosine x minus, all right, and then we have sine of x times 1 all over x squared. So there's that one. Now if we want to take the derivative again, then we have to either, now with this one, check this one out. This is a mess. You have to use the quotient rule, but within the quotient rule, you'd want to use the product rule. Now, of course, we could separate this into two fractions. This does equal x cosine of x over x squared, and we could reduce that minus sine of x over x. Now, we already did that one too, so this actually comes out to be cosine of x over x minus sine of x over x. Isn't that neat? But anyway, so then we could just do, we already did this one. So if we, yeah, that's the answer. So when we take the derivative, get the second derivative, that would match up. But if we don't take the derivative, we don't split this up and simplify this, and we went about doing this without this, you're gonna, well, like I said, we have the quotient rule, but inside the quotient rule, there's the product rule. And just to show you, because that one would actually be the easy one, and so I don't want to shortchange you. So let's say f prime of double prime of x. And so, okay, we're in for it. Bottom times the derivative of the top. Okay, when we take the derivative of x cosine of x, we have to use product rule. So that's x times negative sine of x plus cosine of x times 1. F times g prime plus g times f prime. Okay, minus derivative of sine of x cosine of x. Okay, there's that one. Okay, so that's g times f prime. Wait a minute, that's only the first part. Minus f, which is x cosine of x, minus sine of x, times the derivative of that, which is 2x, all over x squared. Squared! Yeah, right? Okay, but if you take a look, so we got 2 of those, and we got 1 of those, and we have 4 of these. Okay, so we can actually reduce that down a little bit, and so we're going to end up with x cubed on the bottom. And so now we have this, and so now we can distribute, so we have negative x squared, because x times x is x squared, sine of x. This cosine x minus that cosine x, well, that's 0. Nice. And then over here, minus 2x cosine of x, because we have that 2 out there. Negative times negative is a positive, so plus 2 sine x. And so we would get there. That'd be our second derivative. So that's where we get on that one. This one would actually produce a very similar thing, except for a little bit different, So, but it would still come out to be the same concept. So, yeah, all right. So give some of these problems a shot. I'm going to put them on make sure I'm put them on. I wrote it down. So I got my list going. So yeah, all right, give it a shot. All right, talk to you later.